Our next lesson in Chapter 9 is Lesson 9.4, ellipses. An ellipse is an oval shape, so it's kind of a stretched circle, either vertical or horizontal. To define an ellipse in our standard form for a second-degree equation, when you take a look at the two quadratic terms, you'll notice they'll be separated by addition, but they're not the same. This is how you can tell the difference between an ellipse and a circle. To write an equation of an ellipse in standard form, we have two types. And I apologize that this is blurry. I cut this from another note packet and it didn't copy very well. So I apologize for that. If you take a look at the equations, there's some unique characteristics that make them different looking than a circle. First, you'll notice you've got fractions. So we have x squared over b squared plus y squared over a squared. Over on the right, we have x squared over a squared plus y squared over b squared. Now the difference between a squared and b squared, a squared is always greater than b squared. That's going to be significant. The bigger denominator defines the type of ellipse you have. In the first equation, notice the bigger denominators under the y-axis. That will make your shape vertical. The ellipse will be taller than it is wider. It's really that easy to tell. In the equation on the right, notice your a values under the x squared, and that makes your ellipse horizontal. That means it's wider than it is taller, almost like a football that fell over on its side. Now let's go back to that vertical ellipse. The major axis would be the y-axis. So instead of calculating your center and then going right, left, up, and down in four directions like a circle, now you're going to go up and down whatever the square root of the number underneath the y value is for the major vertices. For the minor vertices, you'll take the other number's square root and you'll count to the right and to the left. It's actually pretty easy to do when you see an example. Now over on the right, if we flip the a squared and the b squared, and have a horizontal ellipse, now your major axis is the x-axis. And you take the square root of that number for the major vertices. Here you'd count to the right and to the left. To then get the minor vertices, you would count up and down by whatever the square root is above or under the y variable. For graphing purposes, let's find these specific key features. The first thing you want to do is graph the center. We determine the center just like we did with circles. If x squared and y squared are isolated, your center is 0, 0. And then we'll figure out our major vertices and graph them. And those will just be two dots on the graph. When we graph the minor vertices, we'll still have those 4 points around the center, but they'll be different lengths away. And then we just kind of sketch that oval shape, which would be the form of that ellipse. All right, let's try a couple of examples on the right. In the directions, it says graph each ellipse, state the type, the major axis, minor axis, center, and vertices. So what we'll do is we'll state the type. We don't have to state each type of axis, but we'll state the center and those vertices. Those are also known as our key features. We have x squared over 25 plus y squared over 9 is equal to 1. Notice the bigger denominator is underneath the x squared. That means our major axis would be the x-axis, and this is going to be a horizontal ellipse. That would be the type. To find the center, we take a look at the numerators. Notice x squared and y squared have nothing being added to or subtracted to them in a parenthesis. That defaults our center simply to 0, 0. To get our major vertices, if the number underneath x squared is 25, that's the same as 5 squared. So to get those major vertices, we'll just call them major, we're going to go 5 to the right from the center and 5 to the left. That would be 5, 0 and negative 5, 0. And then we do our minor vertices, and those come from the other number. The number underneath the y is 9, and that's the same as 3 squared. From the center, we would go up 3 and down 3. That would be 0, positive 3, and 0, -3. All right, let's go down to our graph and plot those 4 vertices and the center and see what our shape looks like. First, we'll start with our center and our major vertices. 0, 0 for our center, and then I'll count 5 to the right and 5 to the left. To plot our minor vertices from the center, we're just going to go up to 0, 3 and down to 0, -3. All right, take a moment and connect those 4 vertices to form the shape of the ellipse. And your ellipse should look something like this. Notice it's not quite a circle. For our second example, we have x squared over 12 plus y squared over 36 is equal to 1. Notice the bigger denominator is under the y squared this time. That makes this shape a vertical ellipse. So maybe a football that's standing end to end. Notice up above with x squared and y squared. Our center would be 0, 0. That's one of our key features. For our major vertices, I don't know if I wrote stars last time. I like writing stars. For our major vertices, 6 squared underneath the y, or 36 is the same as 6 squared. But because it's under y, our major vertices are now going to go up 6 and down 6. So 0, +6 and 0, -6. To get the minor vertices, notice the number underneath x squared, this time isn't a perfect square. So if we know that it's 12, we would have to take the square root of 12. The square root of 12 isn't a perfect square, but it has a perfect square factor. So we have to kind of remember those rules from chapter 4. That breaks down into 4 times 3, and the square root of 4 is 2. The exact location would be 2 square root 3 to the right and 2 square root 3 to the left. Notice when we plot our center and our major vertices, we've got 0, 0, and then 0, 6 up top, and 0, -6 down below. But to get 2 square root 3, we're going to have to approximate to find that location on our graph. If you plug in 2 times the square root of 3 on your calculator, you would get approximately 3.5. So what that means is I'll count 3.5 to the right and put a dot, and then -3.5 to the left and put another dot. So now try to connect these 4 vertices for our vertical ellipse. When you're finished, hopefully your ellipse looks something like this. Truth be told, I had to draw this like 4 different times because my stylus pen wasn't getting me to all the vertices on this graph. But hopefully your graph looks something like this. Like circles, we're able to translate the center for an ellipse as well. And we do the same format, translating by the ordered pair h, k. A couple of things to note. The a squared in the denominator will still be greater than b squared. We look for that to determine the type of ellipse we'll have. Notice in that first picture, a squared is under y, so this is going to be a vertical translated ellipse. Your center, as you note on the picture, is HK. The major axis is the y-axis. Now, if it's vertical, we're going to move the center up and down. Watch how I write my major vertices. We're going to keep H the same, and then we'll add A to move it up from the center, and we'll subtract A to move it down. And that will give you your major vertices. The minor vertices are that B value, and we'll go to the right or to the left. What that means then is we're going to take our H and we'll add B to move it to the right, and then we'll subtract B to move it to the left. Truthfully, it's the same thing we did with our center at 0, 0. It just looks different because the new center is at h, k. When the bigger numbers underneath our x and we have a translated center, again our center goes to that HK location, but now our major axis is the x-axis, which means we're changing the x-coordinate to get our major vertices from the center. Take whatever a equals from a squared and move it to the right and left by adding it to h and then subtracting it from h. Those minor vertices are going to change the y value. So count from the k part of the center up b for the top minor vertice and then down b for the bottom vertice. Okay, let's try a couple of translations. For each equation, state the type, major axis, center, and vertices. Again, we can cross off the major axis for this one. These are just identifying our key features, and then we'll sketch the graph of the ellipse. In that first example, part A, x plus 2 squared over 9 plus y minus 1 squared over 16 equals 1. We know this isn't a circle because we have fractions and the denominators are different. Technically, our A and B capital letters would not be the same. Based on that, look at the bigger denominator. It's 16, and that's underneath the y variable. That's going to make this ellipse vertical. All right, let's go ahead and find our center. Remember, our center takes the opposite sign as we translate both the x and y coordinates from 0, 0. If it's x plus 2, our center will go to negative 2. Y minus 1 means it will count up 1. And there we go. Our major vertices, we'll take our 16, which is the same as 4 squared. And from the center, we'll count up 4 and down 4. And it looks like this. Negative 2. If we do 1 plus 4, that would be negative 2, 5. If we count down 4, 1 minus 4 would be negative 2, negative 3. Those are our two major vertices. To get the minor vertices, we use the number underneath the x. That's 9, which is the same as 3 squared. We'll count 3 to the right and 3 to the left from our new translated center. If we do negative 2 plus 3, that would be positive 1, making one of our minor vertices 1, 1. And if we count 3 to the left, whoa, I just wrote that wrong. Hang on. From our new translated center, count 3 to the left, and that would put us at negative 5, 1. We have our center and our 4 vertices. Let's go ahead to the graph down below and plot them. Notice I've plotted my center at negative 2, 1, and I went up 4 and down 4 to negative 2, 5, and negative 2, negative 3. For my minor vertices, I went 3 to the right and 3 to the left at 1, 1, and negative 5, 1. Last but not least, please connect your 4 vertices to form the shape for your translated ellipse. And your ellipse should look something like this. It should look a little bit taller than it is wider. And I think we'll stop here and finish the rest of our notes in class.